we are moving to the fifth chapter. Okay, this chapter is the atomic structure. Okay, this starting of this chapter in our textbook is in the page of 295. Okay, there are several subtopics under this chapter 5. Okay, let's look at to the structure of an atom. Okay, we have learned this in the first chapter. Okay, that we know atom is the smallest unit of a chemical element. It is the smallest one. Okay, and then there are three subatomic particles in an atom. Okay, in which we have a proton, we have a neutron. Both of these are located in the nucleus of an atom. Okay, proton and neutron in the nucleus, and we have a electron that is moving around the nucleus of an atom. Okay, these are three subatomic particles that we have in an atom. Okay, so if we look at to the title, it is atomic structure. So we are focusing on what we have in an atom. Okay, so this is the model of an atom. This is the modern model of atom. Okay, if we observe that we have this atom, okay, in which we have a tiny point at the center of this atom, and that is actually the nucleus of this atom. And if we zoom in, we observe that we have a proton and neutron in it. Okay, while the electron is actually outside the nucleus, it is moving around the region of an atom. Okay, so 5.1, okay, that's just the introduction just now. Okay, 5.1 we'll discuss on the atomic orbital. Okay, so what is the atomic orbital? Atomic orbital is a 3D space in region around the nucleus where there is a high probability of finding electron in that space. Okay, so orbital is the 3D region in space around the nucleus. It means that we have a nucleus at the center. Okay, and then we have a space, 3D space around it. Okay, we know that the atom is 3D, right? We have a y-axis, z-axis, okay, and x-axis. Ke depan, ke belakang, ke atas, okay, kiri dan kanan. Okay, that is 3D space, 3D region. So that if we have a nucleus at the center, okay, then the orbital is actually like the room for the electron. Okay, because this is the space around the nucleus where there is a high probability of finding the electron. So that the electrons will be in this region, in this space. Okay, in this 3D space around the nucleus. Okay, so there are four types of the atomic orbitals. Okay, but what we will discuss the three types that we covered in our syllabus. Okay, so let's look at the first type of the orbital, which is the s orbital. Okay, so s orbital have a spherical shape. Okay, the shape of the s orbital is spherical, which is the same shape as the atom. Okay, spherical, in which we have a nucleus at the center. So this is the example of the 1s orbital. Okay, this is 1s orbital. We have a nucleus at the center. Okay, this is 2s orbital. Nucleus is at the center of this 2s orbital. So that the probability of finding the electron at the distance r from the nucleus are the same. Okay, from all direction means that the probability of finding English. Okay. The probability of finding the electrons are the same from all directions. Okay. And we will get this s orbital when the L value is equal to 0. Okay, what is L? We'll discuss later. But you have to remember, okay, we'll have the s orbital or this spherical shape orbital when the L is equal to 0. Okay, and then as n increases, the size of the s orbital increases. Okay, this is the second letter. The first one is L, second is N. Okay, when N value increases, the size of the orbital will increase. Look at this, we have 1s, 2s, 3s. Okay, this is the size of 1s orbital. 2s is bigger, 3s much bigger than 1s and 2s. Okay, what makes their size different even though they have the same shape? Okay, the same shape because they are all s orbital. Okay, but why they have different size? Because of this n value. This is 1s, 2s, 3s. 1, 2, 3, they are what we call as the n or principal quantum numbers to be discussed later. Don't worry. Okay, but s orbital is when we have a spherical shape and the nucleus at the center. Okay, then the second type of the orbital is p orbital. We'll get this p orbital when the L is equal to 1. Okay, remember L just now when we have s orbital? S orbital is when the L is equal to 0. Okay, and then when L is equal to 1, the type of the orbital is p orbital, and this p orbital has a dumbbell shape. Okay, it has two loops. Okay, as for these p orbitals, okay, there are three orientation in space. Okay, if you look at to the orbital in the textbook, starting from the page of 314, okay, and then the shape of orbital 319. Okay, look at to 319 for the orbital. Okay, this dumbbell shape of the p orbital has three orientation because we know that we have a nucleus at the center here. Okay, and then we have atom. This is actually atom. Okay, atom is 3D space. So we know that we have X, Y, and Z axis. So when the loops, okay, when the two loops is on the Z axis, look at to this Z axis. When the two loops on the Z axis, so we identify or we label this p orbital as pz. Okay, why Z? Because it is on the Z axis. Why p? Because this is a p orbital that has two loops. Okay, and then if the two loops, okay, lies on the x-axis. Okay, see this is the x-axis and the two loops on it. Then this p orbital is px orbital. As if the two loops on the y-axis, then the orbital is py. Okay, so we have three orientation in space. Tiga kedudukan dalam ruang. Okay, it's either dia on the y-axis, z-axis or x-axis. And these three orientation of the p orbital in space is actually corresponding to the m value. See, this is the third letter, m, the third type of the quantum numbers. Okay, m equal to -1, 0 and +1 will leads to three orientation. Since that we have 3m value, we will have three orientation in space. Okay, it is the same as the s orbital just now. When the n increases, the size of the orbital will get larger. Okay, let me show you. Okay, how when n increases, the size will be greater. Okay, if let's say this is the x-axis. Okay, and we want to draw and differentiate the 2px and 3px. Okay, so we will have two lobes on the same axis. This is 2px. Draw the first lobe and the second lobe. Okay, the size should be the same. Okay, and then if we label this as 2px, so 3px will be greater than it. Okay, and have the same center, which is the nucleus here at the center. Okay, the nucleus is here actually. Okay, and then we label the second orbital here is as 3px. What's the difference between these two orbitals is at the n value here, 2 and also 3. Okay, and then if let's say you have to draw 4py. Okay, so for py orbital, so if let's say this is y-axis, so 4py will be greater than the size of 3p and also 2p. But it is lies on the y-axis, so you label this as 3py. Okay, but still they are actually based on the same nucleus because okay, we are having the same atom. Okay, they are all in an atom. Okay, all these orbitals are actually in an atoms. Okay, now let's look at to the third type of the orbital. Okay, it is d orbital. Okay, we start with S, and then we have p orbital with 2 lobes, s orbital spherical, and then d orbital is when we have 4 lobes. Okay, ada 4 cuping. Okay, ada 4 balloon, that is lobes. Okay, there are 4 lobes for 4d orbital, and another one d orbital has only 2 lobes that along z-axis, that is on z-axis, with the donut shaped girdles at the center. Okay, we will have this d orbital when L is equal to 2. Okay, just remember s orbital L 0, p orbital L 1, and then d orbital when L is equal to 2. Okay, so d orbital has 5 orientation in space. Ada 5 kedudukan dalam ruang around the nucleus. Okay, that is corresponding to 5 ml value. Okay, the ml value is -2, -1, 0, 1, and 2. Since that we have 5 value, 1, 2, 3, 4, 5 ml value. Therefore, we will have 5 orientation of the d orbitals in space. Okay, which is corresponding to dyz. Okay, dxz, dxy, dx square y square, and dz square. Okay, so let's look at to the first one. Okay, dyz. Okay, how to differentiate or identify that this is dyz orbital. So when the 4 lobes are between y and z axis. Okay, so look at to the axis. This is y-axis. This is z-axis. When the lobes are between, okay, all these 4 lobes are between these 2 axes. Okay, it is not on. Okay, they are all between the axis of z and y, so that the orbital is the yz. Okay, but then if the 4 lobes are between x and z axis, okay, this is the x axis and z axis, x, z, so that the lobes between these 2 axes, then the name is the xz. If the lobes between x and y, it is the xy. If the lobes on, okay, this time the lobes on the x and y axis. Okay, look at to this x, we have 2 lobes on it. Okay, and then y-axis, we have 2 lobes on it. Okay, so that the name of this d orbital is dx square y square. Okay, and then the last orientation of the d orbital is dz square. Okay, so this dz square, how to identify it? It has only 2 lobes that lies on the z-axis, and then it has a donut shaped girdles at the center. Okay, this is a special one. Obviously, that we can identify that it is the z square. Okay, if I try to draw on my own, okay, to differentiate. Okay, if let's say this is x-axis, this is y-axis. Okay, so I want to draw the dxy, so that the lobes between this axis. Okay, their shape and also size should be the same. Okay, so since that the loops between these two axes, okay, they are between it. So we know that this is actually the XY orbital. Okay, however, if we have a loops on X and Y, okay, they are on X and Y. Okay, so they are what we call as the X square, Y square. Okay, between it will be the X, Y. Okay, if let's say you want to draw the XZ, okay, the XZ, okay, you can use the same axis. Okay, you just label differently X and Y. So now you turn it to X and Z. So this orbital now become the X, Z. Okay, because the loops are between X and Z axis. We know that they are 90 degree to each other and they are not static. They can roll, kan? Okay. So you can change the axis as long as they are 90 degree. Okay, that is the third type of the orbital, and the last type of the orbital is actually F orbital. Okay, the last one is F orbital. Okay, in which F orbital is when L is equal to 3. Okay, so for the F orbitals, okay, they will be 7 orientation in space. Okay, however, for our level, we do not cover it in our syllabus. Okay, but if you want to see the example of the F orbital, it is in a figure 7.20, page of 322 of the textbook. Okay, that is for the orbitals. Okay, so the orbital is actually, as I said just now, it is like the room for the electron. Okay, where is the high probability of finding electron? If we are looking for the electron that is located in an atom, okay, we will look at it in a orbitals. Okay, so if you look at to page 315, figure 7.16. Okay, that's how they define the s orbitals as a spherical shape. Okay, it is like they are analyzing the footsteps of the electron. Okay, so it is like, okay, the footsteps that leave by the electron. We know that the electron is not static, right? Okay, so that when they analyze the footsteps of the electron, okay, then finally they observe that, okay, the electrons are in a space, okay, that have a shape like a spherical. Okay, that is why we have a s orbitals. Okay, same goes with the p and d orbitals. Okay, we analyze the electron. Okay, if let's say this is the electron, okay, finally we observe that their trend, okay, is actually like a dumbbell with two loops. This is for the p orbitals. Okay, but we don't have the end line. Okay, it is not like a balloon when we have a line. Okay, we just draw the shape, or we just imagine the shape based on the movement of the electron. That is why we said that, okay, the orbital is the 3D space around the nucleus where there is a high probability of finding the electron. So the electron, if let's say the electron are the one in the px orbital, Okay, it is very hard to have a electron of the px here outside the region. Okay, the electron will be in this region.